Good afternoon, everyone. This is Dr. Meher Azzouz. I hope everyone is safe and healthy. If there is any technical issue, please let me know. If you can't hear my voice or see my slides or my screen, just let me know. Okay, that is good. Okay, so let's start today's lecture. This is lecture 6 of Power Systems 1. Let me share my screen first. And I want to make sure that the lecture is recorded. Okay, so welcome everyone. In today's lecture, I'm going to talk about two things: three-phase systems and per-phase analysis. So let me remind you about what we have discussed in the previous lecture quickly. So in the previous lecture, we talked about complex power flow, and in the previous lecture, we discussed the factors that affect the power from one bus or from one location to another location through a single transmission line. So suppose we have a transmission line between two systems. So one system is here representing, let's say, the power grid of Ontario, and the other system here represents the power grid of Quebec. Okay, and we want to transfer the power from Ontario to Quebec or from Quebec to Ontario, and we have two components for the power. We have the active power and the reactive power. Okay, so if this is bus 1 and this is bus 2, so P12 is proportional to the angle difference, between bus 1 and bus 2. So this is equal to V1, the magnitude of the voltage at bus 1, times V2 over X12, and X12 is the reactance of the transmission line. For any transmission line, we have different parameters. We have a resistance, because this transmission line is made of aluminum, and we know that aluminum has a resistance, or if it's a cable made of copper, again, it has a resistance. Okay, so we have a resistance, we have a reactance due to the magnetic field around the wire of the transmission line. But in the previous lecture, we discussed that the resistance of the transmission line is much lower than the reactance, and that is why the impedance is approximately equal to the reactance. So the impedance of the transmission line has two components, as we know. It is exactly equal to R plus JX. But if we ignore the resistance, then we can represent the impedance by reactance. We did this simplification to understand the factors that affect the active and reactive power transfer. Okay, so if we ignore the resistance, then the active power between bus 1 and bus 2, or from bus 1 to bus 2, is equal to V1, V2 sine delta 1 minus delta 2. And delta 1 here and delta 2 are the angles of the voltage, So we know now that the power, the active power flow between bus 1 and 2 is proportional to the angle difference, which means if we want to transfer power from Ontario to Quebec, we have to increase the voltage angle of bus 1 with respect to the voltage angle of bus 2. So we will have to make delta 1 greater than delta 2. If we want to buy power from Quebec, or if we want to purchase power from Quebec, then we have to do the opposite, the opposite way. We have to do it the opposite way. We have to increase delta 2 as opposed to delta 1. This is for the active power flow. For the reactive power, Q12 is equal to V1 over X12 times V1 minus V2 cos delta 1 minus delta 2. Okay, Um, the reactive power from this relation is proportional to the voltage difference, because delta 1 minus delta 2 is not a big angle, or it is not actually a large angle. It's a small angle. This angle difference is small, so cosine a small angle is near 1. So this is approximately equal to 1. Okay, and V1 doesn't change that much, so V1 and V2 are around the rated value. Okay, this is due to voltage regulators. So we learned from this relation that the reactive power transferred from 1 to 2 is proportional to the voltage magnitude, which means if we want to transfer reactive power from 1 to 2, then the magnitude of V1 should be greater than the magnitude of V2. I think I got a question. Just a second. Is only V2 multiplied? Look, if we go back to the slides, I hope you can see. Yeah, it is only V2. This is from the derivation. So we started the derivation here. We got the current and we multiplied the voltage by the current conjugate, and we assumed that the impedance is mainly reactive, and that is why we can ignore the resistance. And from this derivation, we ended up getting this relation for the reactive power. Okay, that is good. So back to my notes. Okay, so we learned that the reactive power is proportional to the voltage difference. Okay, so if you want to transfer power, reactive power from Quebec to Ontario, then we have to increase the magnitude of V2 as opposed to the magnitude of V1. And I told you this power transfer can work in either way. So for example, if Ontario has surplus active power, then Ontario may sell active power to Quebec. And if Quebec has surplus reactive power, then Quebec can sell reactive power and buy active power. Okay, so this is happening by controlling the magnitude of the voltage and also the angle. Okay, as we will learn in maybe the next lectures, maybe in 2 weeks or 3 weeks, we will learn the phase shifting transformers or the regulating transformers. Those regulating transformers allow us to regulate the voltage magnitude and also angle, and by doing so we can play with the power transferred between two buses. And the project, by the way, I asked the GA Abdullah Abu Naga to actually assist me in developing a course project for you guys. The course project is about power factor correction, regulating transformers. Okay, so you will learn, you will see by simulation how the angle change, the active power transfer, how the voltage magnitude affects the losses and the reactive power flow through transmission lines. So this is pretty much what we have explained in the previous lecture. There are a lot of details about complex power flow and how the maximum power is proportional to the voltage squared. So the amount of we call it the power capability, or the maximum power that can be transferred over a transmission line. So if you double the voltage, of the transmission line, we can increase the amount of reactive power by 4 times, which is 2 squared. So if you double the voltage, the maximum power transferred, which is calculated by this factor, this is the maximum power, okay, will be increased by 4 times. And this will help us reduce the need for land to install transmission lines, decrease the power density of the transmission line. But of course, as you double the voltage, you have to double the height of the tower, because as I told you before, we use the air to act as an insulator between the line and ground. So doubling the voltage means we have to increase the height by double, which of course adds to the cost of the transmission line, the cost of insulators, but we save costs in terms of the land requirements, or building a double circuit to serve the same load. Okay, so this is a quick summary of what we have discussed in the previous lecture. In today's lecture, I'm going to talk about three-phase systems. So this is lecture, I think, number 6. I think lecture 6. So we're going to talk about two things: three-phase systems and pair-phase analysis. Okay. Yeah, this is again, yeah, it's we save money in the amount of towers we build. This is true, but again, increasing the height of the tower increases the maintenance cost and other things, the cost of insulators, because as we double the voltage, we have to use better insulators in order to make sure, like the insulators, I told you the air, we use the air to insulate the voltage, but we have also to insulate the line, okay, from the body of the tower. Okay, so these are other factors that we need to consider when we build a transmission line or increase the voltage. Of course, yeah, it is not a single formula. It's cost benefit studies, like we have to consider we have different factors, as I told you: cost of towers, cost of insulators, and keep in mind, building two circuits increases the reliability. So it is not just increasing the amount of power that we can transfer. So this is a point that I didn't talk about, but let's say, yeah, we increase the voltage, so we could increase the power. But what happens if we have a fault here? If there is an animal contact or a tree flash over, we didn't trim the tree limbs and branches, and as a result, a tree limb comes in contact with the line and causes a short circuit. So in this case, we have to trip the line. We have to disconnect this line. If we have two lines, then the other one can serve at least 50% of the demand, and this increases the reliability and connectivity of the network. Okay, so this is another factor that, or another benefit of having double circuits. Okay, so it is not just about increasing the power. There are other factors related to the system reliability. Okay, so as I told you, we are going to talk about two things today, hopefully, if the time permits: three-phase systems and pair-phase analysis. So let me start. Okay, so this is what we see, in rural areas or on highways. We see three-phase system. Like for example, this is phase A, B, and C, and the wire that you see here is the ground wire. This is the ground wire, and this is the power pole. And you see here insulators. So these are the insulators, like they are here. So in order to provide insulation between the body of the tower and the line itself, we have to connect insulators, as you can see here. Okay. So these are the three phases. So let's discuss the advantages or the benefits of having three-phase systems. So we can transfer more power for the same amount of wire. So twice as much as a single phase. So what does this mean? So if you have a single phase system, you have a single load, and this is the source. So here we have how many wires? We have one wire, and this is the second one. We have two wires to serve one load. If we have three loads, then we have to increase the cross-section area of the wire or add or equivalently adding a second wire and then a third wire, like this. Okay, so in total, we need 6 small wires, or 2 large ones, 2 large wires. So you can have like a cable of this cross-section area or a larger cable to accommodate the 3 loads. So we can have 3, or I'm talking about like 3 times 2, of course, because we have a returning wire, or we have 2 cables, big cables, to serve these 6 loads. Okay, but in 3-phase systems, you can connect the load as a star connected, something like that, and you use all the 3 wires. If the load is balanced, you don't need to have a grounding wire. But even if we connect a grounding wire, the maximum number of wires needed to serve the same load, the same amount of load, is 4, as opposed to 6. Okay, so this is the benefit. We save the amount of wire needed to serve the same load. Okay, the torque produced by 3-phase machines is constant, so we don't have vibrations or less vibrations. How this happens? Let's go back to the Simulink model we developed in the previous lecture. So here, this is a single-phase system. Okay, we have voltage and current. This is single-phase voltage, single-phase current, and when we multiply the voltage by the current, this is what we get. If you remember from last week. So if the current is in phase with the voltage, we get this single-phase power. So the single-phase power is pulsating. It is not constant. And we calculated the average power, and we named it as the active power. This is the power that is responsible for doing the useful work. And we have another component which is the reactive power. But from what you see here, the active power is oscillating. It is not constant. It is not constant. And as a result, the torque generated by the electric motor is not going to be constant. It will be oscillating, and this will create some vibrations. You may not notice those vibrations, but those vibrations are at 60 Hertz, and they affect, of course, the lifetime of the machine. So this is for single-phase systems. What happens if we have 3-phase systems? So I'm gonna triple this system. So this is VA, B, and then C. So, but I have to do the phase shift. So I'm gonna go here, and I will keep the frequency, but the phase shift is 120. This is negative. We'll discuss this shortly. Okay. So this is the phase shift for the voltage, phase B, and for the current, let's assume it is the same. For phase C, we make a positive phase shift to have a balanced system. Same thing here. I'm gonna name this as A, this is B, and this is C. This one is C. Okay. So we have 3 phases. Let's run the simulation model. The single phase power is oscillating. Same thing here. It is going to be oscillating, but of course, we have the voltage shifted by 120 degrees. Same thing for phase C. The power is still oscillating. But what happens if we connect the 3-phase source to a 3-phase electric motor or a 3-phase machine? In this case, the total power will be the summation of the 3-phase powers. So PA, so this is PA, and this is P phase B, and this is PC. Let's add them together. So if you go to the library and go to summer. So let's use a summer here. We add the three powers together. So this is A. We add it to B, and then add it to C. Okay. And then let's connect an oscilloscope or a scope to see the total power. So this is going to be the total power, P total, which is the summation. Let's see how the total power, which affects the machine, looks like. So let's run this model and see. So look at the power. I'm gonna do some configurations. So let's start from 0 to 1. I think this is constant. It is a little bit number time display. Oh, this is the maximum. I reversed it, so it should be like this. So if you look at the power, this is the scale from 0 to 1, of course, because the voltage is maximum 1, which is the rated value. So if you look at the power, the three-phase power, it is constant. It is not oscillating at all. The three-phase power is not oscillating. If you compare the total power here to the phase power is oscillating. The three phases, if we add them together, let's add them together. So we can use multiplexer like this and inject 4 channels. So we have phase A displayed, B, and then C, and also we display the total right here. Let's run the model and see. Look here, the phase powers are oscillating. So this is phase A, B, and C. These are the phase powers. They are oscillating, but the summation of these powers, the summation is constant, which means the torque produced by the electric motor, the three-phase electric motor, is going to be constant. So we will avoid the oscillations in the torque, and this will, of course, reduce any vibration of the machine. Let me see if I got a question. Oh yeah. So would it be more beneficial to increase the phases? Yeah, there is a question here. Okay, so 3 phases are better than single phase systems, right? This is what about increasing? I mean, the number of phases. Let's say having 6 phases, or 9 phases, or 12 phases. This is a valid question, and it's really excellent question. The problem is that when we increase the number of phases, we increase the complexity of the analysis. And also we increase the complexity in constructing towers. So instead of, for example, caring about 3 wires or 3 insulators, we have to care about 6 insulators and so on. And as you will see, the system becomes very complex when it is unbalanced. The system becomes complex when it is unbalanced. Like here, let me go here, like to the Simulink model. So the reason why don't we go with more phases is to reduce the complexity of the analysis, the complexity of construction. And if we want 6 phases, we can build 2 circuits instead of a single circuit. So here, let's say you wanna have 6 phases. If you wanna have 6 phases, then what you need to do is having a circuit here. Yeah, there is a delay. Sorry about that. You can have 3 phases between 2 towers, or for the same tower, you can actually carry double circuits, like this. So we can have phase A, B, and C, and another circuit here carried by the left side of the tower. So this is 1, 2, 1, 1, and this is the second circuit. Okay. Okay, so this is one of the benefits of 3 phases, is to make the power smooth. If the system is unbalanced, let's see if the system is unbalanced. What I mean by unbalanced, if the magnitude of phase B is not equal to the magnitude of phase A. For instance, so here the amplitude is 1, let's make it 1.05. And for the other phase, let's make it 0.95. And let's run the simulation and see what happens to the power. So previously the power was constant. I mean the total power, it was constant, but now because of a slight imbalance in the voltage made oscillations in the active power. But as you can see, the oscillations are not as high as in the single phase. So in the single phase power, the power oscillates from 0 to near 0.5. So the amplitude of oscillation is 0.5. But here it is limited, but still we have oscillations. Okay, and that is why we try to reduce the system imbalance, try to make the voltages, currents, balance it. And I'm going to discuss all these concepts when I introduce 3-phase circuits. I'm sure that you have studied this in the second year, but it is good to remind you about it and also introduce it from the power system perspective. Okay, so as I told you, the total torque in 3-phase machines is smooth, constant, less vibrations, and that's, I'm telling less vibration. Like I didn't say no vibration. Why? Because if the system is unbalanced, then we will have a slight vibrations as compared to single-phase systems. 3-phase machines use less materials. They use less materials, and they can also start easily, because when we have multi-phase machine or multi-phases, we can generate a rotating magnetic field inside the air gap, a rotating magnetic field inside the air gap of the machine. We don't need to have an auxiliary coil to generate this rotating magnetic field, which happens in single-phase systems or single-phase machines. We don't need any auxiliary coils or windings to help the machine start. Okay. So these are the main benefits of 3-phase systems. Now let's talk about balanced 3-phase systems. I already simulated the system using balanced 3-phase systems. So voltages have the same magnitude, they have equal magnitudes, but shifted with a 120 degrees apart. Okay, and we do this design because we don't want any current in the neutral wire. So if we have the load connected like this, if you remember, the first advantage of the 3-phase system is to reduce the number of wires. Okay, if the system is balanced, then the current through the neutral wire, the returning current will be 0. This happens only if the voltages are balanced, like the voltages are 120 degrees apart, like this. So this is VA, B, and C. And same thing for the current. The current should be 120 degrees apart. This is IA, IB, IB and IC. Okay, and this angle here is the power factor angle. The power factor angle between the voltage and the current. If we have this balanced system, the summation will be 0. The summation of the current will be 0, and we don't need this neutral wire. We don't need this neutral wire. And that is why in high voltage and extra high voltage systems, we use only 3 wires, not 4 wires. But when we approach distribution systems, I mean when the transmission line is near the customers, the cities, the distribution utilities, then we need to have the neutral wire, because loads are not balanced. Loads are not exactly identical. I mean, utilities and power system operators try to balance loads, but at the end of the day, there is an amount of imbalance. And as I told you, a small amount in a small variation in the voltage magnitude will create oscillations in the active power. So we need to have the neutral wire, okay, and we need to size it to make sure that we don't have any problems. Because if we don't connect this neutral wire, then we will have this point floating. The neutral point will have a floating voltage. So ideally, the voltage of this neutral point is 0. Ideally, the voltage of this point is 0. But if there is imbalance, the voltage of this point will be higher than 0 or lower than 0, and will affect, of course, the safety of customers and also the voltage across their loads. So that is why we need 4 wires in distribution systems as opposed to 3 wires in transmission systems. So back to the lectures. Okay, so we know that for balanced systems, voltages have the same magnitude shifted by 120 degrees. Loads are equal. Okay, this is something that we try to do. Utilities try to balance their loads. Like, let's say if they have different feeders and different laterals, they try to distribute the load equally between 3 phases. Okay, and there is, of course, a standard that governs this system imbalance. Like, the voltage cannot be, the voltage imbalance cannot exceed 5%. Okay, lines should be also balanced. So the impedance of line A should be equal to the impedance of the other phases, line B and C. Okay, bulk power systems are almost extensively 3 phases. This is something that we know. A single phase is used primarily on low voltage. This is for distribution. So transmission systems, transmission lines or transmission systems are 3 phase exclusively. Okay, but for distribution systems, when we approach loads, we provide single phase sources. Now let's look at the voltage in the phasor domain. So this is phase A, B, and C, and as you can see, they have the same magnitude and shifted by 120 degrees. We call this sequence A, then B, then C. We call it the positive sequence. We have another sequence which is called the negative sequence. Again, the voltages have the same magnitude, but the shift is different. Like here we have phase B leading phase A and phase C lagging phase A. So if you look here, phase B in the positive sequence has an angle of negative 120, but in the negative sequence it has a positive angle. Okay, the negative sequence voltages or the positive sequence voltages are important when we analyze unbalanced systems, and also this concept is good when we start or when we change the direction of electric motors. So let's say we have an induction motor, a 3-phase induction motor. It has 3 terminals, A, B, and C, and the supply is like this: A, B, and C. If you connect the phases in the positive sequence, if you connect phase A to A, B to B, and C to C, then the motor will rotate, let's say, in the clockwise direction. Okay, but if you switch 2 phases, if you exchange 2 phases, for instance, do this, you connect phase B to phase C and phase C to phase B, then the motor will rotate in the anti-clockwise direction, in this direction. And this is beneficial in many industrial applications. okay, when it is needed to change the direction of the induction motor. Okay, now let's look at the connection of the loads. Loads can be connected as star. As you can see here, we have A, B, and C, and we could connect the neutral point to the of the load to the neutral point of the generator. So the generators, as you can see, have three phases. So three-phase generators generate phase A voltage, B, and C voltages. And if the load is balanced, we don't need this neutral point, this neutral line. We don't need it. But as I told you, most of the loads have imbalance or a slight imbalance, and that is why we need this neutral point to guarantee that the voltage of this point is not floating. Okay. Here I'm going to introduce a new voltage definition, which is called the line voltage. So the phase voltage is the voltage between the neutral and the terminal of the generator, or one terminal of the generator. Let's say terminal A. This is called the phase voltage. But we have another voltage called the line voltage, which is between two terminals of the generator. So this is, for instance, VAB is VA minus VB. It is the voltage between these two terminals. This is VAB. Okay. So if you look at the phasor diagram, and we start by the phase voltages VA and B and C, these are the phase voltages. Okay. By definition, VAB is the difference between VA and VB. So if you apply this in the phasor domain, so this is VA minus VB, so this is VB minus VB, has the same magnitude but in the opposite direction. This is minus VB. So if you add these two vectors together, you get VAB. Okay, so as you can see, VAB has a higher magnitude and leads the phase voltage, which is VA, by 30 degrees. By 30 degrees. So that is why we multiply the positive sequence voltage by √3. This is the increase in the magnitude, and we consider a phase shift of 30 degrees, and same thing for the other phases. Okay. For star connected loads, the phase current, which is the current through the load impedance. So if this is the load impedance, this will be the phase current, I phase. Okay, and as you can see, the phase current is equal to the current through the line. This is the line connecting the generator to the load. These two currents are equal. So if the load is star connected, then the line current will be equal to the phase current. Okay, this is not the case when the load is delta connected, as you can see here. For delta connected loads, the voltage across the load, which is called the phase voltage, this is the phase voltage, is equal to the line-to-line voltage, the voltage difference between these two lines. But the phase current, the current through the load, is not the same as the line current, because the line current, if you look here, the line current is distributed between two loads. If you apply Kirchhoff current law here, so IA is equal to IAB minus ICA. IA is equal to IAB minus ICA. So if you have the phase current like this is IAB, and this is IBC, and this is ICA, and you want to get the line current, let's consider IA. So IA is equal to IAB, this is IAB, minus ICA. So minus ICA, this is ICA, minus ICA has the same magnitude, but in the opposite direction. This is minus ICA. You connect these, the summation together, this will be IA. So as you can see, the magnitude of the line current is greater than the phase current by √3, and it is shifted by 30 degrees in the backward direction. So it is negative 30. This is negative 30 degrees. Okay, this is here the phasor diagram. So I line is equal to I phase shifted by negative 30 degrees, and the magnitude is multiplied by √3. This is for delta connected loads. Okay, and you have always this table to convert from star connected loads to delta connected loads. This is how we convert from delta to star, and this is from star to delta. The first set of equations here, this is for the impedance. The second set of equations is for conductance, and the conductance is the inverse of the impedance. So by definition, Y is 1 over Z. If you have an impedance like this, it has an X and R, Y, which is the admittance, is 1 over Z. Okay? This is useful, especially when we conduct power flow studies to calculate system voltages, currents, and so on. We usually use the admittance, not the impedance of the system. If the system is balanced, then we don't need to worry about this table. This is useful when the loads are unbalanced. But when the loads are balanced, then it is very simple. The equivalent star impedance is equal to the delta impedance divided by 3. Okay, so if you want to convert from here to here, this is what you need to memorize. And of course, I'm going to provide you with a formula sheet. The exams will be take-home exams, so you have all the equations, under your, observation. You can use whatever equation you want, but again, the system that we are, or the systems under study in this course are balanced, not unbalanced. So this is good for unbalanced power systems. Okay, here we deal with balanced power systems. Okay, now do you have any questions before I solve an example? Let me see. Okay, that is good. So why it is good for why is it good for unbalanced system? Okay, yeah. Okay, so let me go back to the slides. For unbalanced systems, loads are not even. So for instance, ZA, the impedance of phase A, does not equal ZB or ZC. So in this case, you have to use the generic equations to switch from delta to star. But for balanced systems, ZA is equal to ZB and ZC. And in this case, if we are dealing with delta connected load, it is going to be equal to Z delta. So it is very easy to switch from delta to star using this simple equation. But if the system is unbalanced, then we have to use this generic equations. And that is why I'm telling you, increasing the number of phases will increase the complexity of system analysis. So if we switch from 3 to 4 or 6 or wherever, this will add a lot of complexities. And even nowadays, when they invented the DC transformer, I mean a power electronic device that is capable of stepping up and stepping down DC voltages, the analysis is way easier than AC systems. If we have DC systems, you don't need to worry about the reactive power. This is very simple. Like in AC systems, let's say we have a line between two nodes like this. This is a power supply, Ontario, again, same system, Ontario and Quebec. We have two components for the power. We have the active power and the reactive power. This is for AC systems. But when we deal with DC systems, we don't have reactive power. We don't have reactive power. The power will be constant. The power will be constant. Also, we don't need to worry about oscillations in the active power. We don't need to worry about oscillations in active power because the power remains constant. There is no like phase A and B and C or if the load is unbalanced, or all these things will not affect the DC system. Okay, and we will be dealing only with the resistance of the line, because the inductance of the line in a steady state, as you know, for DC systems, is equivalent to a short circuit. In the steady state, the inductance will be a short circuit, and the capacitance will be an open circuit. Okay, this is for DC systems, of course. No, like for this course, we'll not be dealing with unbalanced systems. In power systems too, we will discuss unbalanced systems during contingencies, faults, and so on. So we'll be using negative sequence voltages, zero sequence voltages, currents, and all these things. So in this course, we'll not be using the negative sequence or the zero sequence. The focus of this course is to use the positive sequence components, which I introduced in the beginning of this lecture. But we have two sequences, the positive sequence and the negative sequence. In Power Systems 1, we'll be using the positive sequence. Power Systems 2, we'll be using all sequence components, positive, negative, and zero sequence. Okay. Okay, so let's go back to the slides. Okay. Now, let's solve this problem here. We have a balanced positive sequence, Y-connected voltage source. This is a balanced voltage source. The voltage, the line-to-line voltage is 480 volts with angle 0, and it is applied to a balanced delta connected load. A balanced delta connected. So the balanced load has an impedance of 30 ohms, and the angle is 40. The line impedance is given. We have the line impedance. Calculate the line currents. So we need to calculate the current through the line, the delta connected currents, and the voltages at the load terminals. So we need to calculate the voltage here, okay, and the current through the delta connected loads. So the first step is to get an equivalent line to neutral diagram, because this is a balanced three-phase system. So we can solve the circuit from the perspective of phase A only. From the perspective of phase A only, and then after we get voltages and currents for phase A, we can, if needed, we can get the equivalent voltages and currents in the other phases, phases B and C. Okay, and this is called the per phase analysis. The per phase analysis. One phase is enough. It is a good representative to the other phases. Okay, so the first step, okay, is to convert delta connected load to their equivalent star connected loads. This is the first step. Okay, why? Because we need the line to neutral diagram. The line to neutral diagram. For delta loads, we don't have an impedance from the line to the neutral. So that is why we need to convert the delta impedance to the equivalent star impedance. All sources, okay, has to be connected from neutral to ground. So in this case, if the voltage is given as a line-to-line voltage, then we have to get its equivalent line-to-ground voltage. We solve one circuit, let's say phase A, and then we generalize all. We map everything to the original circuit. So let me solve this problem. I'm gonna switch to my notes. So I'm gonna keep this here and switch my notes. Okay, so we have the load. This is ZY, the equivalent star connected impedance, which is 10 with angle 40. The line has an impedance of 1 with angle 85 degrees, and the source here should be line to neutral. So we have EAB, this is given. EAB is 480 volts with angle 0. So we want to get EA neutral. So EA neutral has a lower magnitude, so 480 divided by √3, and should be shifted backward by 30 degrees. So this should be 0 minus 30 degrees. And this is due to the phasor diagram which I explained before. So we have EAN, and we have this simple circuit. This is the simple circuit, like we have an impedance representing the line, an impedance for the load. So the line current will be this current, IL, or let's call it IA. So IA is equal to the voltage divided by the total impedance. So we have ZL plus ZY. This is the first step. Okay. Now, this current will supply the equivalent star-connected load. So this is the equivalent star-connected load. But in reality, the load is connected as delta, like this. So this IA should be distributed between the load impedances. So we need to get IAB. IAB. This is IAB. There is a relation between the line current of delta connected loads and the phase current of delta connected loads. And in this case, we have to divide the line current by √3, and the angle here, should be increased by 30 degrees. Let me remind you quickly. It's here. Look, if you have the line current, the phase current of the delta connected load has leads the angle, leads the line current by 30 degrees. So it has a higher angle, and the difference is 30. So if the current here, let's say, has an angle of, the output here, angle of negative 73. So the phase current leads by 30 degrees, so we need to add 30 degrees to this amount. And that is why you see negative 43.7 degrees. The magnitude of this current is divided by √3 to get the magnitude of the phase current. Okay. So this is how we get the phase current. And then we need also to calculate the voltage across the load. So the name of this voltage is VA. So the supply voltage is EAN. The voltage across the load is VAN. Okay. So to get this voltage, you apply Kirchhoff voltage law on this simple circuit. So we get this equation. So VEN is equal to EAN minus IA times ZL. And this is the phase to neutral voltage, phase voltage. Let me write it like this. This is phase to neutral. Okay, but this is not the voltage needed, because in three-phase systems, the default voltage is the line-to-line voltage. So we have to get VAB. We have to get VAB, and we know if we have the phase to neutral voltage, you need to multiply this by √3 and increase the angle by 30 degrees. And this is what you see here. So I calculated the phase to neutral voltage and then multiplied its magnitude by √3 to get the line-to-line voltage and increased its angle by 30 degrees. Okay? So when you solve the circuit using the single line diagram or the line to neutral diagram, you need to keep in mind, okay, what is the nature of the load, what is the connection of the load, how to switch from phase to line or from line to phase. Okay, this is a good example to explain how three-phase systems, or how we analyze balanced three-phase systems using line to neutral diagrams. Okay. For power, in the beginning of this lecture, I introduced how we calculate the power. So if you have three-phase voltages, three-phase currents, the total power is the summation of all phase powers. So this is PA, B, and PC. But of course, these are instantaneous. I think I got a question. Could we approach? No, we cannot approach this problem using the delta connect. We have to transfer delta connected loads to star connected loads to work per phase. Like, you know, if you want to calculate the phase, like the phase to neutral voltage, the line current, and all these things, everything we should transfer. Look, the idea here is to transfer the three-phase circuit to a single phase circuit, because we used to deal with single phase circuits. This is the idea. We cannot transfer, we cannot keep the delta connected loads. We have to switch them to star connected loads and then convert the three-phase circuit to an equivalent single phase circuit to analyze. Okay. Okay, good. So the power imbalance of three-phase systems, we have three voltages, three currents. We multiply voltages by currents to get the phase powers and add them together to get the total power, and this is the instantaneous power. At the end of the day, the total power is going to be constant. It will not have any oscillations, as we saw in Simulink MATLAB. If you look here, the total power is given by this formula. Sorry. So 3 times the phase voltage times the phase current cosine, sorry about that, cosine theta, and this is the power factor angle, the voltage, the angle difference between the voltage and the current. Same thing for the reactive power. It is similar to the single phase, but we multiplied by 3. And as I told you, by default, in three-phase systems, we use three-phase powers and line-to-line voltages. So we use three-phase powers. So for instance, if I tell you we have a three-phase motor of 100 kilowatt and a voltage of 4 kilovolt. So these numbers are related to the three-phase power and the line-to-line voltage. Okay, so this is the default interpretation, or the default values for the default ratings for three-phase systems. So in this case, we need also to express active and reactive powers using line-to-line quantities. Okay, so if you go back and revisit the relations between phase voltages and phase and line voltages, phase currents and line currents, we end up getting this relation. So instead of 3, we multiply by √3, and we use line voltage and line current. The angle remains the same. The angle remains the same. Okay, I already introduced the per phase analysis, which is basically we need to get the equivalent line to neutral diagram. Okay, there are steps, of course, to do that. We first, you need to convert delta connected loads to star connected loads, line to line voltages to line to neutral voltages, and so on. And this is valid only for balanced three-phase systems. We cannot use the per phase analysis for unbalanced systems. If the system is unbalanced, we have to deal with every phase separately, phase A, B, and C. Okay. And here we assume no mutual inductance between phases. So, for instance, let's say we have 3 lines. This line has a self-impedance and mutual impedances. Like, there is also a mutual impedance between the lines, Z mutual, and this is ZS. This is ZS, the self-impedance. So so what we do, we neglect the mutual impedance, or we solve the problem, or we analyze the system using the sequence components. Sequence components. So if we use the positive sequence voltage, I'm going to give it a different symbol. B positive, okay, and B negative and B zero. Then the coupling between phases will be eliminated. There is, of course, a derivation behind that. And in this case, if we eliminate the coupling, then we can still use the bare phase analysis. Okay. So for this course, you don't need to worry about all these details, but I'm explaining the assumptions. So first, loads, lines, everything should be balanced. And also we need to eliminate all mutual impedances between lines, between phases and loads and generators, which is the case in most of the power systems that we study. Typically, the standards do not allow systems to be unbalanced beyond 5% threshold. Okay, so we can analyze them bare phase, and the results we get will be close to the actual results. Okay, now these are the steps. We can solve example number 5. I mean, again, to explain, I mean, the bare phase analysis. Already, I discussed all these steps before. So let's begin with this example. Another example here. But in this case, we have two loads. We have a delta connected load and a star connected load. The voltage here is the line voltage, VL. It is 207.85 volts. The line impedance is given. It is here. We got the impedance. We got the impedance of the loads. So here we represent loads by their impedances, not by their power consumptions. And I'm going to solve two examples. One, which is this one, the example number 5. Here we represent loads using their impedances. In the next example, I'm going to represent loads using their power consumptions, which is realistic in many situations in power system analysis. Okay, so let's see how we solve this problem. The three-phase balanced source has this. Okay, so the first step, we have a delta connected load. This delta connected load, we need to convert it to its equivalent star connected load. So here we have an impedance. This is Z star. I'm going to call it Z star dash because this is Z delta over 3. The other load is star connected, so you don't need to worry about it that much. So you just use its impedance. So the impedance of the second load is Z star. And then we have a line, and Z line is given. This is example number 5. Z line is 2 plus J 4 ohms. And we have the source. Okay. The voltage of the source, VA S, is equal to the line voltage, which is 207, divided by √3, and it is specified here to use this phase voltage as a reference. So the angle of this voltage is 0. Okay. We need to calculate the line current. So we have the line current. This is the line current, IA, or our I line, and we have the phase current. We have, let's call it I phase, I star phase, and I star dash. Okay, this is a simple circuit. circuit. You can easily solve the circuit. Like to get the total current, you need to get the equivalent impedance of this circuit. So Z equivalent is ZY times ZY dash over the summation, because these two loads are connected in parallel, and the equivalent impedance is in series with the line impedance. So the equivalent is going to be this. You have the equivalent impedance. Now you can calculate the current, the line current of the supply. Okay, this is going to be the voltage divided by the equivalent impedance. This is going to be 5 with angle 0 amp. This is the first step. If you have the line current and you have also the phase voltage, then you can calculate the power by the supply. So S supply as 3 phase is equal to 3 V phase I phase cos theta V minus theta I, or √3 V line I line cos theta V minus theta I. Okay, we can use the first expression because we have the line, the phase to neutral voltage, we have the phase voltage, and we have also the phase current, because the phase current is actually equal to the line current. So you have these components, okay, and you have the thetas, you have thetas, you have the angle here, which is 0. This angle is also 0. So you can calculate the supply power, which is 1.8 plus J0 kilovolt amp. So as you can see, we don't have any reactive power. We don't have any reactive power. We have all the active power. And this happens because if you look at the second load is capacitive. The second load is capacitive. It has a capacitor bank, as you can see here. So it is capacitive. So this capacitor will generate reactive power to compensate all the reactive power needed for the line and the second load. So the capacitor here will generate reactive power locally to compensate all the reactive power needed in this circuit. And that is why the total reactive power needed from the supply is 0. Okay. Now, we want to calculate the phase voltage, the voltage here across the two loads. So this is V load. We want to get the voltage here between these 2 points. This is V phase load. I think I got a question. Yeah, there is a question here. Why don't we subtract 30? This is a good question. Look, in the given data, they didn't give us an angle for the line-to-line voltage. In the previous example, the angle of the line-to-line voltage was given, and what it was 0. Okay, that is why we like subtracted 30. But here, the angle is not given. Look, the angle is not given. We got only the magnitude of the line-to-line voltage, and it is mentioned to consider phase A as a reference. That is why we assume the angle to be 0 for phase A. Okay. Okay. Okay, guys. So now we got the supply power. We can get the phase voltage here across the two loads. Again, this is Kirchhoff voltage law. So V, I'm gonna use the same colors. So V phase load is equal to VA at the supply minus the current of the supply, of course. You can write it here, it's okay, times the line impedance. You get this phase voltage, and this phase voltage again it is between the line and neutral. if I ask you to get the line voltage at the combined load, you have to convert it. So as you can see here, we got the phase voltage, and it has an angle of -10. For the line voltage, we multiply this magnitude by √3, and we add 30 degrees. We add 30 degrees to this angle. I think there is. I think this should be. This is the. Oh, this is the line. I think, yeah, there could be a typo here. There could be a typo, so I want you to check these numbers. But you got the idea. We add 30 degrees to this angle. Okay, so this doesn't add up. I think there's a typo here, so better check this. I'm gonna highlight it for you guys and check it. Okay, now. So I'm explaining the procedure. Let me minimize this. So you get the phase voltage, and this phase voltage, as we know, is like this. So this is VA. VAB should be leading by 30 degrees. So V line load, you should multiply the magnitude by √3. And add a phase shift of 30 degrees. Okay. I think I got another question. Oh, okay. Okay, so let me move this here and zoom in here. Okay. Now we can calculate. The phase current through the load. Okay, this load originally was star connected. I'm talking about this load. This load was originally star connected. So YI here, the current here, represents the phase current. Okay, so if we go down here, I star phase or phase star can be calculated by applying the current division. So if you have the line current, you multiply by Z star dash over Z star dash plus Z star. You know the current division. If you have two loads, this is Z star, Z star dash, and this is the line current, our line. If you want to get this current, you multiply the input current by the impedance of the other branch and divide by the summation. This is to get I star here, and this is phase. For the other component, which is I star dash in this direction, you can also get it using the current division. So I star dash, but I'm not gonna call it phase. I'm not gonna call it phase because this load originally was delta connected, not star connected. So again, you can apply the current division, or simply you subtract I star phase from the line current. You get I star dash, but this is not the phase current. This is the line current supplying the delta connected load. So for I phase delta, or be consistent here, this is I phase star. For I phase delta, what you need to do is to divide this current by √3. Okay, and subtract -30, because if this is IAB, this is IBC, ICA, the line current will be leading by 30 degrees. This is IA. So if you want to get the phase current, which is the line-to-line current, or actually IAB in this case, so you have to divide by √3 and decrease the angle by 30 degrees. Okay, this is how we get the current. again, these two components allow us to get S star and S delta. So we can use these two currents to get S star, I mean the total power consumed by the first load or the star connected load. So it is 3V load, V phase load times I phase star cosine the angle difference. And here, this is same thing, 3V load phase times I. In this case, it is IY dash cosine the angle difference. Okay, so I gave you all the numbers. So as you can see here, we got the power consumed by the star connected load, the power consumed by the delta connected load. The connection will not affect the power. Keep this in mind. The connection will not affect the power calculations. The connection affects the current calculations, the voltage calculations, whether it is phase voltage, line current, and so on. But at the end of the day, the power will remain the same. Okay, for the line power or the complex power consumed by the line. So this is the last thing to calculate. So if you have the total power S supply, this S supply is equal to S line, the complex power consumed by the line, plus the complex power consumed by the star connected load, plus the complex power consumed by the delta connected load. So if you got this power and the other two powers for the loads, then you can get the line complex power. Okay. Any questions? I left, all the answers for this problem. I encourage you to solve this problem. You don't need to look at my notes or my solution. Try to solve it yourself without looking at the solution and compare the results. If there is a mistake or something that you need, you can always go to the lecture recording and check my procedure. Okay, guys? I think, yeah, it is 2:20 now, and the time is actually not allowing us to solve the second example, so I'm going to solve it in the beginning of next lecture. Any questions? Okay, thank you, and have a good day.